that is the agenda. I forgot to mention, EMF is a term that you're going to need to understand, and I'll explain that very clearly for you today too. All right, I've got a bunch of demonstrations that I want to share with you, so try to stay as focused as you possibly can here today so that we can get through this stuff. All right, I'll be asking a billion questions, I promise. So, let me find my clicker, and then we can get started. Look, yesterday we finished the period. It was just about a half hour. We finished the period. Oh, who's missing?
Jenny.
Rena and
Jenny.
Who?
Jenny Zhang.
Jenny. Okay. Do you guys remember?
Someone write it down too. Gosh.
At the end of class yesterday, we were talking about that deflection of the meter in this demonstration. Let me show you something. If I change flux through this coil, if I change flux, magnetic flux through the coil, you see that the meter deflects left and right. The flux is increasing, it deflects one way. If it decreases, it deflects quite the other. Okay? What we're going to try to do today is to get to the bottom of what this deflection is. Yesterday at the end of class, we determined that the deflection thing was proportional not only to magnetic flux, but to how fast that magnetic flux changed. Okay? So that's where we left off yesterday. Do you guys recall that? And I showed you this magnetic induction example with the galvanometer. So, here's what I'd like to do. I want to show you what this actually is, what this deflection thing actually is, and then we'll develop Faraday's law from that. All right? Now, I showed you yesterday that magnetic flux can be calculated by multiplying two vectors together, B times A. And I want to talk about that real briefly before we get any further. All right? If you can imagine placing a vector on this surface area here like that, okay? And think about a magnetic field that might be coming down from the ceiling. You see that if the magnetic field lines are parallel to the vector A, you're going to get maximum flux. And if it's perpendicular to the vector A, you're going to get minimum flux. What function goes from maximum parallel to minimum perpendicular? You guys know?
Is it sine?
It is not. It is cosine. The cosine of 90 is 0. The cosine of 0 is 1. Now, in your textbook, for instance, they'll tell you B times A cosine theta, but sometimes I think that simple is better, and the vector symbol above an area is strange enough that it should remind you that when the magnetic field is parallel to this vector, it's maximum. When the magnetic field is perpendicular to that vector, it's minimum. Charles?
When it says it's some angle to the normal,
Yes.
I mean, it's,
Normal is that vector they're talking about.
but is normal perpendicular?
Correct.
Okay.
Correct. That's what normal means in that context. Yes? Explain what again? Sure. Magnetic field lines are running from the ceiling to the floor, and this vector is always orienting itself perpendicular to the plane of the loop. If the plane of the loop is parallel to the field, you get maximum flux. Cosine of 0 is 1. If you rotate it so that they're perpendicular, the magnetic field lines and A are perpendicular like this, you get minimum 0 flux. Okay? And so A times B times the cosine of the angle between them will give you the actual amount of flux, should they ever be either something other than 0 or 90. Sure, normal means perpendicular. Okay? Now, you guys a while back, I don't know, probably a week ago or so, I told you that I would ask you one day to put it back in your notes. You remember that day?
I got
Here
this.
we are. I would like you guys to remind me for a moment what the unit for the magnetic field is.
Tesla.
Very good. Well, okay, I should do that first. Tesla. How do we measure area? Square meters, very good. And then what's the metric unit for time? Seconds. Like that. Now, David, what's the unit for Tesla? Right. I asked you to tell me that, remind me that a Tesla was actually a Newton divided by an amp times a meter. Do you remember that, Dave? Here we are, already here. That's how time flies. Very good. Yep, there it is. Now watch. I still need to go meters squared in seconds here, and so I can now clean up for the first time by doing this. Very nice. Okay? Now, here's another question. Musang, you can help me with this one. What is an amp actually measuring? What does an amp measure? Okay, and when you measure current, what are you actually measuring? Very good. Speak up. How much charge is traveling through a part of a circuit per second, isn't it? So, what's the actual equivalent of an amp then? Q over T. Very good. And Q is measured in coulombs, isn't it? So look at this. I'm going to go newtons times meters. The seconds flips up here to the numerator, doesn't it? Coulombs, seconds. Clean up to the third time. Now, yes. Oh, we popped in coulombs per second for an amp. Oh, and so coulombs per second. And then you can recognize this. What is it, Jay? That's a joule, isn't it? So this becomes a joule per coulomb. Hold on there, fella. Who can remember what a joule per coulomb is? Jay knows? Anybody else know? What a joule per coulomb might be? Do you know? Or are you guessing? Huh? Alex?
Yes, I do.
What is it?
It is a volt.
It is! Ladies and gentlemen, what we have here is voltage. This thing is the unit for volts. Now, if you think about it in the context of this demo, it shouldn't be too surprising. Because what is this actually measuring? This is measuring current, and what produces current? Voltage does. Remember, voltage is I times R, isn't it? From our circuits unit. So if we have a conductor of the product of voltage is current. And so when I do this, I'm generating voltage. Changing flux is generating a voltage. That voltage in a conductor is producing current. You guys with me? Now, let me say this. If I take a wooden hoop like that, and be very careful when you answer this question. Don't just give me a knee-jerk reaction. Okay? This is a wooden hoop. If I change flux through it, will that generate a voltage? No. That's a knee-jerk reaction. It really is. Seriously? Give me your wrist.
Now.
No. There it is. I wanted to hear the spin. Now listen. Listen. Think about what I asked you. I asked you if it will create a voltage. What's the criteria for generating voltage? Changing flux through a closed loop. Did I change flux through a closed loop? You bet I did. The difference is, this thing conducts charge, this one doesn't. The electrons in this respond to the voltage, this one doesn't. The electrons in here just going, stop that. I can't move. You see? So that's why you have to think about it before you answer. Does this meet the criteria of this deflection? Yes, it does. Yes?
Are we assuming that like the loop is area? I don't know.
Just a closed loop.
Oh, what does that
Just a
mean?
closed loop.
What does that mean?
That. It's not a trick question.
Okay.
It
No,
could
I
be
know,
this.
I was-
It could be this. You know why it has to be closed? Because if it's a conductor, it's got to be a closed circuit. If this is not a closed circuit, charge, you know what I mean, current's not going to flow. Now it would.
Yeah.
You see? Oh, is this for
The
what's
students.
his name? Who's missing?
Jenny.
Oh, what's her name? Hi, Jenny. Okay. Is,
Hi, Jenny.
is that enough to? Is that going to do this whole class?
I don't know.
Probably not.
Yeah, I don't have enough there.
Now listen, voltage is generated when you increase or decrease flux through a closed loop. What the loop is made of will determine whether there is a subsequent current flowing in it. Itai, what's up? Huh?
Never mind.
He wanted to say hi to Jenny. Hi.
Birthday
Listen.
boy.
Listen, listen, listen. Changing flux through a closed loop generates voltage. What the loop is made of will determine whether current flows or not. You see the difference? If I hook this thing up to my wooden loop, which I put over here, you're not going to get any reading because this thing's reading current. It's not reading voltage. Look. But it certainly is generating voltage. The charge just can't respond to it, so you're not going to get any current. This depends on the material it's made of. This depends on whether flux is increasing or decreasing through a closed loop. You guys with me?
No,
What's the matter?
I don't understand the difference.
This deflection is a measure of voltage. All right? It's voltage. It's joules per coulomb.
Alright. So that's how much voltage.
Yes, if the material is a conductor, that voltage can produce current in it. Just like we learned in electric
How much
circuits.
of it's flowing, right?
Yes,
Okay, that's just eight.
that's the battery part of it.
Okay.
What?
Or what happens if it's not a conductor?
It's like if you hook up a battery to a wooden circuit.
So like, so it'd be like.
When you connect your fingers to a 9-volt battery, nothing. Too much resistance. You're not a conductor. No charge flows. Well, then charge flows because that's a conductor. All right. Now watch. You guys, look at this thing. E. E. Look. E stands for a special voltage that's derived from changing flux. They call this EMF. For electromotive force. Listen, batteries produce voltages by virtue of chemical charge separation. This is fundamentally different because you're actually physically moving charge with a magnetic field. That's the QVB force, isn't it? QVB. There's a force acting on moving charges in magnetic fields. That's what's happening here. So they like to differentiate between this kind of voltage and your run-of-the-mill, everyday household battery type Duracell battery voltage. Okay? This is V, this is E. It still follows that this thing can generate a current just like Ohm's law does, but we just want to differentiate this from this. We don't have to, but we do. And that is going to be equal to something times the rate that magnetic flux changes through that closed loop. Okay? I wanted you to leave 2 spaces because I've got spaces to fill in. All right? The first space here
There we go.
has to do with this versus this. Pretend this is a copper wire for now, just for a minute. Okay? You guys, do you think that there would be a difference between me changing flux through a bunch of these versus only a single one?
Yes.
Of course there is. That's why they do this. If I change flux through 100 loops versus 1, you're going to get 100 times the voltage, aren't you? That's simple. So look, this thing is going to be just the capital letter N for number of loops. You guys, that's why when they build coils, they do it in the most elaborate ways possible. If you ever take apart the alternator in your car, if your alternator ever goes bad, take it apart and look at the windings in there. Oh my gosh. They make the most intricate series of windings possible. It's really cool. Why? Because the more they can pack in there, the greater the energy they're going to get out of it when they sit there and rotate those coils through a magnetic field. It's fantastic. It's not just a single little loop of wire, believe me. There's intricate windings. The next thing is this.
What?
I know. Well, it is. And you ain't seen nothing yet. All right? Who's missing there?
Send that to side 2.
Cy, Jenny, Rena,
Jay.
Angie.
You gotta be kidding me. This was a meet Andrew. What? You're out here.
Andy.
He's not here. Wait, Jay's actually here. Oh, wait, not Jay.
He's here.
No, Jay. That Jay's here.
Okay. Now look. Look at this. Look at this, look at this, look at this. This thing has a name in and of itself. This thing right here is called Lenz's law. And ladies and gentlemen, I want to tell you something very important. Lenz's law is an application of the conservation of energy as it applies to electromagnetic induction.
Oh my.
I'll get the board later.
It's an application of the conservation of energy. We've gotten to this point today through all of this. Every day we've been here, building up to this moment. Because we had to study the conservation laws, we had to study kinematics, we had to study Newton's laws and vectors and all of this stuff for us to understand what appears to be the most pure and simple thing on the planet, a simple negative sign. But it's not a negative sign, it's not a mathematical negative sign. You'll never use it as a negative sign. It doesn't mean a negative number. It's an application of the conservation of energy. It's telling you that this side of the equation opposes this side. They're in direct opposition. Okay? They're opposing one another. And that is going to be the bulk of our discussion from here on out. All right? Now watch. What I'm going to do is this. I'm going to show you how simple the calculation part of it is. You guys will be able to do that in your sleep. I don't even care that you even see this, but I think it's important to show you an example anyway. Then, I'm going to show you how to find the direction of this, and hence the direction of the current generated as a result of that changing flux. Okay? So, let me show you the boring part first, and then we'll get to the Lenz's law part. Okay? Look at this. If I have a magnetic field, let's say that that magnetic field is directed inward, in toward the the page, into the board like that. Okay? Now, if I take a loop and I move it into the field like this, what I want to do is calculate how many volts are generated in that loop. Okay? It's quite simple. It's a single loop, so we're going to multiply 1 by this thing. If there were 2 loops stacked on top of each other, I'd multiply it by 2. If there were 3, I'd multiply it by 3. If there were 4, I'd multiply it by 4. How many do you think I'd multiply it by if there were 8? Very good. No, it wasn't, was it? See?
It's okay.
Whose birthday? Is it your birthday?
It's my balloon.
He's a princess.
Now watch! Watch this. What I have to do is merely this. I've got to take this and make a calculation out of it. And that calculation is going to be in volts. Alright? Watch this. I'm just going to give you some numbers. Let's say the magnetic field is 2 Tesla. Let's say the radius of this loop is 10 centimeters, like that. And let's say it takes me 3 seconds to move it into the field. 3 seconds to complete all of that. I just go 1001, 1002, 1003. Watch how simple this is. I'm going to multiply. Remember, changing flux is B times A. So it's going to be 2 Tesla times the area of that loop, which is pi r squared. Divided by the amount of time it takes me to do that, it's very simple. Okay? If I start outside the field, the initial flux is 0. If I end up in the field, the final flux is that. And that's all there is to it. Seriously, that's all there is to it. The calculation of this to give you your volts is pretty simple. Okay? Determining the direction that current flows in here, that's the tough part. That's the concept. Listen, difficult concept, easy calculation. Tough concept, easy. Tough, hard, concept, difficult, I got it. So, I don't expect that you guys are going to have difficulty calculating the EMF, the electromotive force, the volts. That is just, boom, V times A over T. Okay? The difficult thing is this, and that's what I want to talk about for the next 50 minutes. Okay?
Hold this.
And then that's what I'm going to talk to you for 70 minutes on
baby.
Tuesday and prepare you as best I can for the test. You ready for this? All right. You sure? Huh? All right. Okay then. Enjoy this.
Yay.
What?